Hey Brian.
Hey, Amar. Hey, Rogelio. How do you pronounce your name? Rogelio? Rogelio?
Oh, you just say Rogelio.
Oh, okay, okay. Sorry about that. Uh-huh. Which reaction are you guys up to like so far? Like, which reaction are you guys familiar with for this new chapter, 17 and 18?
Um, Mascal, I'm might be wrong, but I think Mascal might have covered everything in 17.
I see. Let's see. Up until 17, did he go over the failings test and tolerance test to test for aldehydes?
Um, Let me see. I don't.
Yeah.
What are the reagents in that one?
That is gonna be like the weird like metal ions like copper 2 plus, silver plus
Mm,
thing.
no.
I see. I think that's more of a lab thing, but I think he did go over like Rillig reaction and Bayer-Villiger reaction
Yeah,
with the
yeah, he did.
MCGVA. Yeah,
Yeah,
those are the last reactions there
yeah,
for 17.
with like checking to see if it's tertiary, secondary, primary, like methyl hydrogen, like which is a priority, so you could
Yeah, right with the
use
regulatory
the
aptitude.
oxygen. Yeah,
Uh,
yeah, yeah.
yeah. See, are you familiar with those reactions, or should we go over those practice problems and the whole mechanism reaction as well?
Yeah, I just mainly wanted to just like go through the mechanisms for like all of them,
Okay.
just because like Mascal, when he
Yeah.
does his mechanisms, like I didn't understand how to do proton transfer at all until I went over it today. Because like he
Oh,
just he just wrote proton transfer, and then like
yeah.
he always just like draws like through the mechanism arrows. He just does like minus H plus or like plus this. Like he doesn't actually show what's going on.
Right. He skips those steps like I know he expects you to know it like from the first time. But the common pattern that you follow for these proton transfer steps is that you deprotonate the group that you want to stay, and then you protonate the group you want to leave. And this proton transfer pattern here is for most of the mechanisms in this chapter, like forming an acetal, going backwards to the carbonyl, the imine, the enamine. It follows this pattern here with the proton transfer. So, which mechanism do you want to go over first? Do you want to go over all of the mechanisms, like the acetal one, forward mechanism, reverse mechanism, imine,
Um,
enamine?
if we could, do you think we could go through them like we can go through them like pretty brief, like
Uh-huh.
run through them, but like
Yeah.
just like yeah,
Okay. I'll go over the forward to the cyclic acetal and then backwards, and then let me know, like stop me when I like don't make sense. Right. So
okay,
let's say
for sure.
we have this carbonyl here. If we put that carbonyl through this diol, like the two alcohols there, where does the CH2 and CH2 separating those two under some kind of acid catalyst. The acid catalyst could be H2SO4, H3O plus, or even HCl, a non-nucleophilic alcohol. So I'm just gonna use H2SO4, but you could also use H3O plus. What
Mhm.
you're going to get is this cyclic acetal here, where this is an acetal because that carbon there has two OR groups, O, R,
Mhm.
O, R, and specifically a cyclic one because it's in a cycle. So the first step of the mechanism is to protonate the carbonyl oxygen here. What that would do is that would activate the carbonyl carbon, right? This
Okay.
carbonyl carbon was partially positive because it is attached to the electronegative oxygen. But once we activated it by protonating the carbonyl oxygen, imagine that this oxygen here wants to get neutralized by stealing its bond like that, making this carbon to carbon a bigger partial positive charge because oxygen here is now like more greedy for its electrons to
Yeah.
become neutral. Now, that strong electrophile is now able to be attacked by this weak nucleophile here. This is a weak nucleophile because it's neutral. There's no negative charge. That weak nucleophile was not able to attack this weak electrophile, but the weak nucleophile is able to attack a strong electrophile. So this
Mhm.
is called the activation step where we activate the carbonyl. We're going to attack that carbonyl carbon, pop the double bond onto the oxygen, and get this intermediate here. And all of these arrows I'm drawing are reversible because we could go backwards.
Right.
Alcohol, new bond between that carbon and oxygen attacked it, CH2, CH2, OH. And this oxygen here that attacked the carbon still has a hydrogen bond there. Right? 3 bonds on the oxygen, positive charge. Now, this is the point where we do the proton transfer step, like the plus H plus minus H plus step, where it follows the deprotonate the group we want to stay, which is this group here, and then protonate the group we want to leave, which is that group there. This is a good leaving group because it has a positive charge. To make that into a bad leaving group, we have to deprotonate it. So it cannot leave. We want it to stay.
Yeah.
Right. Now, this is a neutral oxygen here, where it is a bad leaving group. That's good. We want this OH to leave. To make that into a good leaving group, we protonate it. Right. Now, this is a good leaving group where I'm going to draw this in one step, but imagine the leaving group leaving. There's going to be a positive charge on that carbon right there as that leaving group leaves. Like a carbocation gets formed. Like think of it as an SN1E1 reaction. Leaving group leaving, carbocation gets formed there, where this lone pair of electrons on oxygen can make a double bond there through resonance. Right? Another way you could think about it is that to drive that leaving group off, we're going to reform the carbonyl and then kick that leaving group off at the same time.
Okay.
Like that. Right? So what we get is that carbonyl, oxygen, CH2, CH2, OH. This oxygen has 3 bonds, positive charge. Side product, water, the water group that left here. Right. This is another activated carbonyl, but in the next step, we're going to do an intramolecular reaction where the alcohol at that end is going to attack this carbonyl carbon,
Are you large
pop
or
to the
extra?
bottom to the oxygen, and then we're going to form a 1, 2, 3, 4, 5-membered ring like that. Right.
You're not gonna fit that. It's
So
not like a-
what we're going to get is this structure here, positive charge. And then the last step is just to neutralize that oxygen by deprotonating
You
it.
have my remnant time.
Like that.
Oh, what are you doing here?
And we reform our acid catalyst there.
You live here? You look at my, the meeting, really?
Okay.
Right.
Okay. Yeah, that makes sense.
Yeah, a lot of these are proton transfer steps, acid-base reactions, which follows this pattern here.
Yeah, I think Mariah followed like
Oh,
yeah, she
Pap-Ched,
said
right?
yeah,
Yeah, proton.
EAPT, ED, and then when you make the acetyl, you add an extra addition because you're doing it like twice, unless you're making the hemi acetyl.
Yeah, yeah. It follows that reaction as well. PAPTED and then that extra thing.
Yeah.
Mhm.
So technically, this would be like the same for making like a regular acetyl.
Yeah.
If it wasn't like I think she referred to it as like tethered, the OHs, like if they weren't.
Tethered
Okay.
together, right? If they were separate alcohols, then that would make acetal that is not cyclic, right?
Okay.
The difference is that this right here is an intramolecular reaction where it forms a ring here from the intramolecular reaction. If it wasn't
Okay.
tethered together like that and they were separate, then an intermolecular
Yeah.
reaction would happen, like
If it were
another
like
alcohol.
some ROH, and then you'd have 2 equivalents react.
Yeah, yeah.
Okay. And then with sulfur, I'm assuming the mechanism different with sulfur?
Yeah, it is different with zinc, metal, and stuff like that.
Yeah.
But I don't think
Yeah,
you
I
need
don't
a
think
mechanism.
yeah, I don't think we need to know either because he was saying like you can make various like byproducts from the mechanism or like the reaction. Just
Right.
know it like does the same thing.
Yeah, yeah, that's the same thing. And usually it's given like as an extra CH2 bond, like this. Like we have 3 CH2s here, CH2, CH2, CH2. But you
Okay.
could also do it with 2 CH2s only like this, which would give you this instead. Right. Where to go backwards, these are the reagents you need to use. HCl2, CaCl3, CH3CN, water. Those 4 things, chemical soup.
Got it. And then what about for the cyclic acetyl? If you want to go in reverse of that.
Yeah, to go in reverse, water and acid, H2O
Okay.
and some kind of acid, H2SO4 or H3O plus.
Got it.
Right. Do you want to go over the mechanism of going backwards as well from the cyclic acetal to the carbonyl?
Is that like typically something that can also
Yeah,
be like
that is
tested?
typically tested as well, like the cyclic
Okay.
acetal to the
Okay,
carbonyl.
yeah. Sure, we
Yeah.
can take a look at that one. So
Let's go. So if we want to go from a cyclic acetal to a carbonyl, we want to use water. And let's say this time we use H3O plus. First thing we do, we make this into a good leaving group by protonating it. Once we have protonated it, that's a good leaving group. Where this is probably the confusing part for most people. Whenever we have that and we reform a carbonyl, that's the driving force for the leaving group to leave, right? Because like some people don't get how like this can just happen by itself, but it doesn't happen by itself. When it happens, it also kicks out a good leaving group at the same time, right? If it just
Mhm.
happens by itself, that's gonna break the octet rule because we're gonna make a 1, 2, 3, 4, 5 bond on the carbon, which breaks the octet rule. When we remake that double bond, we have to kick something out, which is that good leaving group there. And that leaving group doesn't entirely leave the whole molecule because it's still attached to this oxygen here. It just
Yeah.
breaks open the ring into the linear form. Where this oxygen with 3 bonds, we have a positive charge there. And then in this activated carbonyl, we use the water nucleophile to pop the double bond onto the oxygen. And then at this point, at the tetrahedral intermediate, we do that pattern. Deprotonate the group you want to stay, protonate the group we want to leave. We want this group to stay because we want the carbonyl back. We want this group to leave because we don't want that group anymore. To make this into a bad leaving group, we have to deprotonate it. And make it neutral. To make this group into a good leaving group, we have to make it positive charge by protonating it. Now, this is a good leaving group where this is the part where people get confused, like how does that leave? It leaves by this driving force here. The carbonyl gets reformed from the alcohol, kicking out the leaving group at the same time. Or another way you could think about it is that the leaving group could just leave first by itself, like an SN1E1 manner, forming a carbocation at that carbon. And then from that carbocation, the resonance structure would be that this lone pair of electrons goes down to form the carbocation, to form the carbonyl. But
Hmm.
we could just do this at the same time without drawing the resonance structure. Right. So that would create this carbonyl with the hydrogen, positive charge. The side product would be this diol here, that tethered diol to alcohols. And then the final step, neutralize that oxygen by deprotonating. Right. So this will be like following Le Chatelier's principle as well. If you want more of the carbonyl form, add more water to the reaction. If you want more of the cyclic thioacetal, add more diol to the reaction.
Okay.
Nice. Okay. Let's go over imine and enamine now. So an imine will come from either ammonia or a primary amine.
Is that just
So,
yeah.
uh-huh.
I was just gonna say is that RNH2, but you wrote it down.
Yeah, RNH2. Right. Secondary one would be,
The enamine.
Oh yeah. It would create the enamine. Right. I was asking like what would the what would the secondary amine look like in the general structure, which is R2NH.
Oh,
R2NH,
okay. Yeah, yeah.
Yeah, but right, that secondary amine, the R2NH would give the enamine, right? So let's say we have this carbonyl, and we put this under a primary amine like this here. These reactions will always happen in acidic conditions. So let's say we put H2SO4. The reason why is because we need to activate this carbonyl here,
Mhm.
right? In the mechanism, I have to check what Pascal does because different professors do things differently. Uh,
I could.
yeah.
What's the specific question about it?
Like what gets protonated first, the amine or the carbonyl oxygen?
Let's see.
Because the nitrogen here is actually more basic than this oxygen here.
Okay, so he used NH2R in the first step. He protonated the oxygen.
Oh, okay. So he protonated this oxygen here. He doesn't protonate this nitrogen first, right?
No.
Okay, that's good. Because Nasiri does it that way first, and then from that protonated version, he protonates the oxygen by that protonated version. But that's an extra
Okay.
step that we don't gotta
Okay.
worry about.
Is Helix do it the same way as Pascal?
Yeah, Helix does it the
Okay.
same way as Pascal, protonate the carbonyl oxygen. So I wasn't sure.
Okay.
Yeah, right. Activate that carbonyl by using the strong acid. Which makes it into a good electrophile, strong electrophile for this weak nucleophile, which is neutral, to come and attack, pop that double bond onto the oxygen. OH, N, and then R group, and then it's two H's. And then at this tetrahedral intermediate point here, we follow the same exact pattern for proton transfer. Deprotonate the group you want to stay, protonate the group you want to leave. We want this group to stay, so we gotta deprotonate that group using the conjugate base. And make it neutral, bad leaving group. Right. Now, once we create that bad leaving group, we want this OH group to leave. So to make that into a good leaving group, we gotta protonate it using the strong acid.
Okay, so all these reactions pretty much follow that same pattern.
Right. Follow the same pattern. It's just a lot of proton transfer steps.
Yeah.
But in this point here, we don't form a carbonyl. A carbonyl is a carbon double bond oxygen. We form an imine with the I.
Yeah.
IMINE, which is a carbon double bond nitrogen. And then kick out that leaving group. Right. But you notice how it's like the same thing as the last mechanism, just different
Mhm.
nucleophile. Okay. And this nitrogen with 4 bonds will have a positive charge, where the last step is to neutralize it by deprotonating it. And the side product that gets kicked out is water. Which gives us our imine.
So you lose your H's in the process, right? You lose two
Yeah.
H's.
Right, you lose 2 H's in the process, in the whole mechanism. The first H was lost by deprotonating it the first time to make it into a bad leaving group. And then the second H was lost by neutralizing the final product. Right. But in the overall process, we lose 2 H's in the amine. Right. If this was an ammonia, like NH3, 2 H's will still be lost, giving this as the answer if you have ammonia, like the imine with the 1 hydrogen left. Right. Instead of the R group. Okay. This also is reversible. Do you want to go do an example of going backwards here using water and acid?
Is it like the same as the other one?
Yeah, it is the same like the other one where you first have to protonate this nitrogen, make that into a good electrophile, and then the thing that attacks it is water, and then you get that tetrahedral intermediate, and then do the proton transfer, and then go all the way to the carbonyl.
Okay, I think it's fine then. Yeah.
Right. Now let's go over the enamine because the enamine one is a little tricky at the end. For enamine, you need a secondary amine, which is R2 and H. Right? So let's say we have this carbonyl, and we have this secondary amine here in H2SO4 acid. First step, activate that carbonyl, make that into a strong electrophile. Once we activated it, we use the weak nucleophile, the neutral amine, to attack, pop the double bond onto oxygen, get the tetrahedral intermediate. Now at this point, we do the proton transfer step, deprotonate the group we want to stay, which is this amine group, by deprotonating it and making it neutral. Yeah, there's a lot of steps in this mechanism, but it's like
Yeah,
it follows the
it's
same.
yeah, the same pattern.
Yeah. Now we want this OH group to leave, but right now it's a bad leaving group. To convert it into a good leaving group, we protonate it and give it a positive charge. Now, at this point here, this drives the good leaving group off by forming the iminium ion, kicking out that good leaving group. And then we get this iminium ion here. Now, at this point, we're used to deprotonating the nitrogen and making it neutral, but there are no protons on that nitrogen to deprotonate. Like, there's no hydrogens attached to that nitrogen at all. It's just R groups, R group, R group, R
Mhm.
group. To neutralize this, we gotta do an elimination kind of reaction where we get one of the alpha hydrogens and we use the base to come in, deprotonate that alpha hydrogen, make a double bond there, and then basically like imagine kicking out the leaving group, but it doesn't get fully kicked out because that's a double
Yeah.
bond there.
It pushes the double bond, the pi bond to make it a lone pair,
Right, and neutralize the
not neutralizes it.
right lone pair of electrons comes from that one bond right there that pushes up. Right, and then we also get an alkene here,
Okay.
which is our enamine. So an alkene next to an amine, enamine.
Okay. And then just in
Like
general, yeah. In
Yeah.
general, are any of like these compounds, like I remember he said something. I remember in lecture, I forget which one he said, but he said one of them was like very unreactive. But is that like the basis of like most of these? Like you can't really do much with them. Like maybe with this, would the alkene be reactive? And like if you wanted to
Oh,
do anything with it, or like are
so
these typically
this
like
right
stable as
here,
they are?
think of this as an enol, right? Like imagine instead of this amine here, we have an alcohol here. This is gonna act similarly to an enol by having this alpha carbon nucleophilic. So we could like reform the imine bond and have that alpha
Hmm.
carbon attack an
Okay.
electrophile. And then that's like the rest of chapter 18, like what I'm gonna go over tomorrow.
Yeah.
Like alkylation of the alpha carbon from an enamine instead of an enol.
Okay.
Right. Chapter 17 is just setting up for chapter 18, where it explains like the alpha carbon aldehyde ketone and then what it could do. And then chapter 18 expands on it by introducing more reactions like Aldol, Michael, Robinson, and then alkylation of the alpha carbons from an enol, enamine, and the other things that we made in chapter 17.
Okay.
Mhm.
Wait, Brian, I have a question.
Yeah.
Is there any way like you could reverse like the enamine or imine back to a carbonyl?
Yeah, there is. All of these steps are reversible. Do you want to go do both like reverse mechanisms from imine to carbonyl and enamine to carbonyl?
Or like would it be like is there like a certain reagent? Like is it just H2SO4 and H2O?
Yeah, it's just H2SO4 and H2O. And the H2O oxygen is the carbonyl oxygen. The water oxygen is that oxygen of the carbonyl. The H2SO4 or H3O plus is just an acid catalyst that gets like remade in the mechanism. It gets used up and then remade at the end.
Okay, okay. Yeah, I just wanted to make sure if you could like revert it back to a carbonyl.
Yeah, you can.
Okay, okay, thank you.
The tricky one here is probably the enamine, like going back to the carbonyl. Right. So we're used to, like, if we look at the imine here, if we want to go backwards, you would just protonate the nitrogen imine, right? And then activate the imine, and then the water attacks it, and then we do that whole proton transfer thing. And the enamine one, we don't protonate the nitrogen. We protonate the alpha carbon by first forming the iminium ion, and then using that alpha carbon to get protonated by the acid. And then once we have that like positively charged iminium ion, then we use the water to attack it, and then we do the whole proton transfer step. So that's the difference between the enamine and imine first step,
Oh,
going
okay.
backwards. Yeah.
Okay. So
I think
basically, so like you'd still like no matter what, you're gonna need like H2O and SO4, H2O or like some acid catalyst.
yeah. All these reactions are in acidic conditions. The reactions we did today in the content review, like the Aldol, Michael Robinson, all those reactions happen in basic conditions.
Okay.
Uh-huh.
Okay, thank you.
Yeah. Let me just go over the mechanism of going backwards from enamine to carbonyl really quick, because that's the different thing at the first step. Water, H2SO4. We don't protonate the enamine nitrogen. We protonate the alpha carbon, which gives our activated imine bond right away, where the water can then attack that strong electrophile. The weak nucleophile water can attack the strong electrophilic iminium ion. And then from here, everything is the same. Right? Where the biggest difference is this right here. You don't protonate the enamine nitrogen, you protonate the alpha carbon from an enamine. Right, so let me just do that here. We want the alcohol, oxygen, we want the oxygen to stay, so we gotta deprotonate that group. And do all this. Wait, I think this is why Pascal like did the plus H plus minus H plus, because like he was so tired of doing all these things like one by one
Yeah.
every time. But that's not good. Like teaching for the first time, like once people get it, then you could do that like plus H plus minus H plus thing. But teaching it for the first time, that is kind of crazy in doing that. And then the side product here is this secondary amine. We get this carbonyl with its oxygen still. Last step. And yeah, acid catalyst gets reformed. Nice. Let's see. Did he go over the Wolff-Kirchner reduction reaction where you cleave a carbonyl bond to an alkane?
He talked
Um,
about it, but he didn't do a mechanism on it.
oh yeah,
Oh,
he said it's 128 mechanism, I believe.
oh,
Oh
okay,
yeah,
dang.
yeah. I think that's what he said, right?
Bro, yeah, he did, but imagine he pulls that shit out. I'm like, bruh.
Oh my God. It is on the one of the content review notes though. I posted the mechanism for that.
What would like the predicted products look like for, can you just do that like really
Uh-huh.
quick, like an example?
Yeah. For predicted product. There's like in different forms, it could be like predict the product, predict the reactant, or predict the reagent, like on the arrow.
Okay.
For
Yeah.
predict the product, let's say it was something like this. Um, And the reagent for Wolff-Kirschner, you can see it in like different forms. You can see as NH2, NH2, or H2N, NH2. These are all the same thing, or N2H4. Like these are the ways that I've seen it given, but they're all the same thing. And then you also have NaOH, water, and heat. What that will do is just completely find the carbonyl and cleave it off to get the alkane.
Oh, right. Yeah, I remember him talking about this.
Right. I don't think he could give you a problem on like predict the reactant from this, because if he gives something like this and then he gives you like the reagent, let's say N2H4, NaOH, water, and heat, your carbonyl could be here, it could be here, or it could be here. So there's multiple products, reactants from this.
Okay, I see. So it's not regioselective in that sense then.
Yeah, not regioselective in that sense. Right, right.
Okay.
But he can give a predictor reagent question on
Yeah.
this. Like that. Where if you see a missing carbonyl, then you know this is Wolff-Kirschner.
Got it.
Wait, do you think it'd be possible if he asked because we learned a new instead of PCC,
Mhm.
it's like a weaker oxidizing. I think it's a weaker oxidizing agent, MnO2.
Oh, right. Yeah. Did he teach that in class? MnO2, the manganese oxide
Wait,
oxidizing
did
agent?
he?
I look, you forgot. I wasn't really paying attention in lecture.
Yeah. Let's
Has
see.
that been a question though, Brian? Like that you've gotten like in tests?
Yeah. That is a question that I've gotten tested before. And I've seen like people got tested on it as well before. Right. So let's say we have this kind of structure. And then we use a weaker oxidizing agent than PCC, which is MnO2. What this would do is only oxidize allylic or benzylic alcohols. Right. So once you have this like polyol reactant, like a lot of alcohols, you first determine which ones are your allylic and benzylic alcohols. So let me just say this is A, B, C, and D. Which ones are allylic and or benzylic?
B and D.
Yeah, B and D. A and C are too far away from the benzene or alkene, so those will not react. No reaction for those alcohols. We only oxidize the benzylic or allylic ones into the carbonyl. This alcohol stays the same, no reaction there. This alcohol stays the same, no reaction there. This allylic alcohol gets oxidized to the carbonyl. And what do we form here?
Oh,
We've What is that? What is that one thing? We talked about it today. Isn't it like a conjugated?
Yeah, alpha beta unsaturated carbonyl or enone.
yeah,
Yeah.
enone.
Which is an electrophile for what kind of reaction?
Oh,
The Michael
Michael
addition?
addition.
Michael
Yeah.
addition. Yeah.
So this could be
Um,
synthesis. Like if you do
yeah.
MnO2, you create this kind of enone, and then you could do Michael addition.
I have a
so that's
question.
Mhm.
So what if you had a primary alcohol and it was benzylic or allylic? Would that take it to an aldehyde or would it take it to a carboxylic acid?
a good question.
MnO2 would take it to, huh? uh, let's see. I would guess aldehyde, but let me double check on that for you. Yeah,
Okay.
that is a good question. That's a good question.
Just because it also would make sense that the aldehyde, just because we're saying that it's weaker than PCC and only
Yeah.
Jones takes primary alcohols to
carboxylic acid.
carboxylic acid.
Right. Primary allylic alcohol with MnO2. Yeah, just an aldehyde. It takes it to an
Okay.
aldehyde. It stops at the aldehyde.
Okay, cool.
Yeah. Mhm. And then from this, you can convert it to the carboxylic acid by further oxidizing it using the stronger one, Jones, or the new reaction you learned,
You can do a
Bayer
Michael
Villiger,
addition.
MCPBA or RCO3H. You can also do a micro addition from this enone here, but that micro addition would not create a carboxylic acid. It will create a 1,5 dicarbonyl, like where
Oh
there are two
yeah.
carbonyls 1,5 to each
Yeah.
other. Where in this Bayer Villiger reaction here, we're going to insert an oxygen between the carbonyl carbon and either this group or that group there. He didn't. I remember someone formulated the migratory aptitude list. He just said it was tertiary over secondary over primary over
Yeah.
methyl, right? But
Yeah.
that's not the complete list. The complete list
Maria
is
said, yeah, hydrogens
hydrogen,
take
yeah,
precedence.
and then tertiary, and then phenyl. Oh no, not phenyl. Um,
Oh yeah,
Secondary
secondary
and
and
second
phenyl are equal.
Yeah.
chlorhexane, and then secondary is equal to phenyl, and then primary, and then methyl. Right. This is the more complete list that I've seen
Oh,
compared to this one.
cyclohexane on there. I didn't even see that one in Maria's video.
Isn't that
Yeah.
a benzene?
This is a phenyl.
No.
I mean the cyclohexane. No double bonds in there. The benzene is the phenyl here.
Oh,
Right. This is
I didn't see that.
cyclohexane. See, that's CY. You could abbreviate that as CY, cyclohexane. Let me make sure because I got this from Edna's notes when I took the class, but let me see just to make sure. Bayer
Did you
Villiger.
have Helix or Nasiri for B?
Nasiri for
Nasiri.
B, yeah. And I think you guys have it worse because I think Mescal is worse than Nasiri.
Really?
I
Yeah,
don't think
yeah.
so.
Oh,
I
I
like
really?
honestly think I like Mascal more than besides the vocab.
Yeah.
I don't know. I feel like his reactions are easier than Levin's. Like I had a harder
Oh,
time with Levin's reaction
mhm.
than Mascal's,
Yeah,
especially the
yeah.
synthesis too.
Right. Yeah, that part, the reaction to synthesis part is like oversimplified, like
Yeah.
compared to Nasiri's and Levin's, but it's just
Yeah,
the
with the
vocab that I
vocab.
hate.
Yeah, that's all I lost my points on. Besides
Yeah.
not drawing the resonance in the mechanism from the most recent midterm, it
Uh-huh.
was just
Bro, he never
vocab.
asked for it. That was stupid.
Yeah, yeah,
Yeah.
that was minus 4% for
Oh my
no
God.
resonance.
He took
Well, that
points
depends on
off
your TA.
for the first midterm, right? Like why he do that? Like if he messed up, then I feel like he should just give you guys the points and not take points off.
Yeah, I don't know.
Let's see, very really good. Yeah. She says the cyclohexane group is in between tertiary and secondary. So and let me give an example on that. If you have a cyclohexane group like that and a carbonyl and let's say a phenyl group, this takes priority over the phenyl group.
What's like the chemical reasoning behind that?
Oh, that I'm not too sure on the chemical
Okay,
reason. I just know like why like what
okay,
happens, but I don't know like the chemical reason.
okay.
Yeah, gotta do
Um,
some like research or reading
yeah.
on that.
And this is more about nucleophiles. Mascal didn't go over it, but like the using like HCN or CN minus to make like the cyanohydride, is
Oh
that like a
yeah.
mechanism
Uh-huh.
that we should know, or
It's
do we just know that it just takes a carbonyl to alcohol with a C triple one?
you should know the mechanism as well. It's very similar to the enamine, cyclic acetal mechanisms that we did. So if we have a carbonyl like that, and then was it NaCN or HCN? I
He
think
used
NaCN.
HCN or NaCN
HCN.
also works too, because I mean it just makes the CN minus.
Right. If you use HCN, then I don't think you need like another acidic thing, but it's probably safer if you do. And let's use H2SO4. So what do you think is gonna happen first if you have these reagents and react in?
The oxygen's gonna get protonated to make
Uh-huh.
the strong electrophilic carbon.
Right. Strong electrophilic carbon. like I'm gonna have you like use the chemical intuition that we've been doing with all the patterns here. Once we create that strong electrophilic carbonyl carbon, what happens next? What's the nucleophile that's gonna attack that?
Cn minus is gonna attack the carbon, and then it's gonna push the electrons up on oxygen.
Right. That's it. That's the whole mechanism.
That's literally it.
Yeah,
Oh, okay.
that's
Interesting.
cyanohydrin.
Okay. That makes sense why he didn't show the mechanism
hmm
then. Okay.
The mechanism for Wittig and Bayer vinegar is really weird and confusing. Like I gotta
Oh
look at my notes
yeah.
every
Yeah,
time.
no, Wittig was really that one was like it was just a pain because it was long, but it made more sense than the Bayer Vinegar because that one was just like it kind of reminded me of Osmosis when you had like five different arrows at once
Yeah, and it does
trying
that
to like
cycler ring.
rearrange.
Yeah,
Yeah.
yeah, yeah.
And
Yeah.
then the thing with Illus that was weird was just like knowing that you have to make the Illid itself first, like a lot of the time, and then do the actual reaction.
Right, right. From the haloalkane.
Yeah.
Mhm. Nice. Right. Because let's say we have this haloalkane and we have this multi-step predicted product. I think it was, yeah, let's do this.
Oh, I hate this one.
Yeah, with the phosphorus.
Yeah.
Did he go over the E and Z product? Like it will mostly be Z if there's no conjugation.
Oh, um,
Oh,
he
maybe
didn't, but
cis, right?
Mariah said that if there was like no alkene, then it would be mainly a cis product, but if there was, then it would be trans. Is that what you're talking about?
Yeah, yeah, that's what I'm talking about. Right, right.
Okay.
It does have to be an
Yeah.
alkene. Yeah, most likely it is an alkene, but it could be a benzene ring, like anything that can do resonance. An alkene is
Okay.
one, a benzene ring is one, carbocation is one, anion is one. Anything that could do resonance would make an E
Okay.
isomer.
And then that would have to be present in the like the original haloalkane
Yeah, in the
or,
original haloalkane or the
or
carbonyl,
okay.
right? Doesn't matter which one. It could be both as well, right? So, what happens first is that this nucleophilic phosphorus is going to attack that carbon, kick out the bromine, SN2. Right. When that happens, this phosphorus with an extra bond will have a positive charge.
Mhm.
And then the second thing here, we have a strong base. That strong base you can see could be either N-butyl or NaOH or NaOR, any strong base. Strong base. And think of this as an elimination kind of reaction where we're gonna deprotonate this hydrogen here, alpha hydrogen. Let's use NaH, which is a hydride ion. Deprotonate that, make a double bond there. You can make a double bond there or actually, yeah, let me just make the double bond there and then show the resonance structure of that to make it more complete. That's going to make a neutral phosphorus with the alkene there, where we can see its resonance structure by drawing this double bond going to that carbon, giving that carbon a lone pair of electrons, negative charge, and that makes this phosphorus have a positive charge because we have to maintain charges in resonance structures, right? But it's easier to predict the product in this form here because what you do in Wittig reactions is that you find your double bond with the phosphorus and three phenyl groups, and you find your carbonyl. And then what you do is you locate that carbon double bond to phosphorus and carbonyl carbon, and then that's where the double bond is. Right? Where this was the red dot carbon, this is the blue dot carbon. It basically merges together, eliminating the phosphorus and oxygen there. Like that. Right? So using this here, let's bring in the carbonyl, the third step, which is going to be this here. We see that there's no conjugation, no alkene or benzene ring on the carbonyl, and like no alkene on the ylid as well, right? There is an alkene here, which is this one here, but that's not the alkene we're looking at. We have to look at the alkene that is alpha to it. So it has to be like that alkene right there in order to get the E isomer, right? Because this alkene of the ylid itself is the alkene of the product that we form, not the allylic alkene or something like that, right? So we located the ylid carbon, which is that red carbon, the carbonyl carbon, which is that blue carbon. Since there's no conjugation, we make the Z isomer. So let's say this is the red carbon, this is the blue carbon. If we want to make the Z isomer, where would these groups go here? Let's look at the ethyl group. Where would the ethyl group go?
It would be on the same side as the methyl.
Yeah, there, down on the same side as the methyl. And then that makes the methyl group on the opposite side. This is the major product because Z, major, no conjugation on ylid or carbonyl. If there is conjugation in either the ylid or carbonyl or even both, then the E is major.
Okay. And then what are those like electron pushing arrows when you have the ylid and the carbonyl?
Oh yeah, the mechanism for that? Okay, let's go over that mechanism as well. Okay, let's do this example that we just did. Okay. So let's say we have this ylid here. We know its resonance structure is this right here. It's easier to see the resonance with the charges on the ylid. So negative charge there, positive charge here. The carbonyl we had was this right here. This is the nucleophile carbon, which is this alpha carbon right there, that is going to attack this electrophilic carbon, pop the double bond onto the oxygen. And then when we draw in the intermediate, we have to draw it in a way where the oxygen is right next to the phosphorus because they make a very strong bond with each other. So this was the electrophilic carbon. This was the nucleophilic carbon here. This is the new bond that gets formed between the star and dot carbon from the attack. When that happens, the dot carbon had a ethyl group and a methyl group. The star carbon had just a methyl group. Right. And then notice how I drew like the bulky groups away from these oxygen and phosphorus right there. The bulkiest groups facing away from the oxygen and phosphorus leads to the Z alkene, the Z alkene major product, because it wants to avoid steric hindrance between the oxygen and phosphorus. So the next step here is this oxygen minus is going to attack the positive phosphorus and form this box-looking thing here. Right. And then we said earlier that the bond between oxygen and phosphorus is very strong. Right, this phosphorus is also attached to 3 phenyl groups. This is where the weird stuff happens. That bond right there goes to there. This bond here goes to here. It's like an electrocyclic kind of reaction. This is where the double bond comes from, where like it just does that, and then this whole thing leaves by itself because it wants to like be together, a very strong bond, stuff like that, which creates this Z alkene here, where we saw that the bulky groups are away from each other to avoid steric hindrance between that oxygen and phosphorus, that's gonna make a double bond.
Okay.
Right. So let's say the carbonyl was conjugated and the ylide was conjugated. Like we had a double bond there. Phosphorus, phenyl. And then let's say there was a conjugation there. Now, think of this as like the endo rule. These groups here, they want to get closer to the phosphorus and oxygen to increase the amount of secondary p orbital overlap. Wait. In this case, it doesn't make sense because if both of these groups are on the same side going up there, that would still be Z isomer. Let's see here. Actually, yeah, just ignore what I said. I'm not too sure of the reasoning why, but when you have conjugation between the ylide and carbonyl, just know that you make
You make the E.
yeah, the E isomer, right?
Okay. Is this like a mechanism also that you see tested on usually or not really as common? Okay.
Not common mechanism that's tested. No.
Okay. Cool.
Yeah. And this is the major product where the E isomer.
Okay. Yeah. And Pascal tends to keep his mechanism problems simple as well.
Mhm.
So
Yeah, probably it's gonna be the common proton transfer ones like imine, enamine, cyclic
yeah.
acetal, or reverse of that to the
Yeah. I'd
carbonyl.
expect that too.
Yeah. Next. Okay. Let's go over the mechanism of Baeyer-Villiger oxidation, which is also weird.
Oh, is that the MCPBA one?
Yeah, that's MCPBA one.
Oh, fun.
Let's say we have this carbonyl and this H. But actually, since Pascal didn't give H, should I do that? I don't know. I don't know if he will put this in the exam like with the H. I'll just do this. There you go. And then RCO3H peroxy acid, which MCPBA is a type of RCO3H. Which one would take priority over the other? Which group?
It would have to be the one to the right because the other one's already has all the bonds, right?
So it doesn't matter. Where this carbon here already has all the bonds, like even though this has
Oh, because
hydrogens,
it's in between.
yeah, it's in between.
Okay.
Yeah, that's the confusing part. This is tertiary, this is secondary. Tertiary wins over secondary. Yeah, in between. Where oxygen is in between the
I
carbonyl
see.
carbon and this tertiary one that wins over, which is gonna be like that. It adds an extra atom there.
Got it.
Right. Positive, and then blue, green. Yeah, in between the blue and green here, in between. Right. This dice is the same. Okay, here's the confusing mechanism that I have to look at my notes every time. I cannot like do it based on like the pattern. Let's
Yeah.
see.
Hopefully there's no testing on this one.
Yeah. Okay. Peroxy acid is a strong acid, so the first step is pretty similar to the previous ones we did. Protonate the carbonyl oxygen. Activate it. Oh my gosh, my iPad. Okay. Let's see. Yes. Okay. After we have activated it, the conjugate base of that peroxy acid comes back to attack the carbonyl carbon. Pop the double bond onto the oxygen. And then I'm going to draw the structure like this, where this was the carbonyl carbon. I'm going to say the tert butyl group, the ethyl group is up here. Tert butyl group is down here. The group that got popped up is this OH here, and I'm going to draw that bond out because this is the weird migration step, like all the cyclic arrows going on. This is the oxygen that attacked of the peroxy acid. Here. Okay. So now we know this oxygen here is partially negative. This hydrogen here is partially positive. That is bonded to an oxygen. So this right here can do H bonds. They are attracted to each other. This oxygen here is going to attack that hydrogen by using one of its double bonds to make a new bond between the oxygen and hydrogen. This bond between oxygen and hydrogen is going to make a double bond there. And then this is the migration step here. We have to choose which R group migrates to this oxygen here. We said the tertiary one wins. So this bond here between the carbon and tertiary carbon migrates to that oxygen there. This bond between oxygen and hydrogen, oxygen makes a double bond right there. Right. So to keep track of everything, I'm just gonna number it like this. 1, 2, 3, 4, 5, 6. And the group that migrates is gonna be this 7th carbon there. Right. So let's draw the resulting products. So this is the ethyl group of carbon 2. This is the thing. This is that. And this is this. And then we also have O. Wait, let me do it this side. O here. OH. R. Where this is atom 1, 2, 3, 7. Right. This is atom 4, 5, 6. Right. Let me make the bond between this oxygen and hydrogen this way so it makes it more clear where this hydrogen came from. Right. Where we see that this whole group here with the 7th carbon that I labeled as 7 is this whole group here that migrated to this 3rd atom. The bond between 2 and 3 is still there, which is this bond. There is now a double bond between 1 and 2 because of this arrow. The ethyl group is still attached to carbon 2. The hydrogen was attached to atom 1, but that hydrogen got grabbed by atom 6, which is this hydrogen here. And then there was a double bond between 5 and 6, but we used one of its bonds to attack the H here, which is that bond now. And then that double bond between 4 and 5 came from that bond between 3 and 4, which broke the thing and created a carboxylic acid here. And the R group is still attached to atom 5 there. But
Damn.
I know, it's very
Big ass
confusing.
mechanism.
I know. But it's shorter than the imine and enamine, like and the forward reverse mechanisms, but it's just trickier to think about.
Yeah, it's just that one step. Like I feel like the mechanism itself isn't bad. It's just the electron pushing arrows in that one step just makes everything bad.
Yeah, this part here.
Yeah.
Yeah.
Like I noticed just the reactions where the predicted products are like stupid easy have the hardest mechanisms.
I know,
Like
I know.
osmolysis and then the hydroboration and then this too. It like
Yeah, I know.
All right. Well, if that comes out, I'm cooked. But thank you, Brian.
Yeah, no problem,
yeah.
guys.
Thank you so much. I'll see you tomorrow.
Yep, see you guys tomorrow.
Yeah.
All right, bye.
Bye. Hey Ryan, hey Zunyan, how are you guys?
Good, how are you?
I'm doing fine. Was today's session helpful? Like, were you able to follow along? Was it helpful for you?
Uh, it's kind of a lot.
I know, no, we went over a lot. We went over the cyclic acetal, imine, enamine, cyanohydrin, Wolff-Kirchner, MnO2 oxidation, Riddig, Bayer-Villiger. Like those guys asked a lot of
Yeah.
questions, a lot of questions from chapter 17, which is good, We basically went over most of chapter 17 in this session here.
Oh, is that content review from today?
Oh, from today, we started chapter 18. From today, we did aldol, condensation, dehydration, Michael addition, and Robinson annihilation. This was content review from last week, chapter 17.
Oh, last week, okay.
Last week. Right. We went over this like with you last week.
Is this all like ketone?
Yeah, all ketone and aldehydes.
Oh, and aldehydes?
And
Okay.
aldehydes, yeah.
Are we like just focusing on ketones and aldehydes from now on?
Yes, ketones, aldehydes for chapter 17, and then for chapter 18, it's the alpha carbon enolate ion. So from a ketone and aldehyde as well. So just ketones and aldehydes everywhere with the alpha
Okay.
carbon.
Okay.
Right. And also imines, enamines, amines, and stuff like that. Those weird things, but they're related to the ketones and aldehydes.
Okay.
Yeah. Yeah. Were you tired today? That's why you didn't show to the content review, or were you
Oh, I went to the animal science barbecue thing.
Oh, barbecue event. I see, I
Yeah,
see.
I have
Uh-huh.
friends graduating, like taking graduate photos. So
Yeah, 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 yeah. I see.
I will be there tomorrow, I
Mm-hmm.
think. I
Okay.
don't
Yeah, that's good. Ah.
When's the final?
The final is 2 weeks from now. Like this is week 9,
Oh,
next week is week 10, and then after week 10 is the finals week. So yeah, somewhere June. Yeah.
Yeah, I should start studying right now, but I'm just too lazy.
Yeah, too exhausted after everything. Like you just had a midterm. Like you need a break.
Yeah.
Yeah.
Well, I think I did well on midterm too, but like I still need like a 70% on the final to get an A.
Oh, you calculated how much you need already. Dang.
Yeah, it's
Ah,
crazy.
gosh. Did you get 70% at least on for midterm too? Or
Yeah, I did.
oh, you
That's
did?
why. Yeah,
70?
72.
Wait, that's an A already, because 65 is an A.
I know, but I did really bad on midterm one. I should have studied more for that.
Oh, wait. Was it above average or below average for midterm one for you?
Just average.
Just average. Okay, I see. And then you got 72 for the second one. You
Yeah.
deserve it because I remember you showing up. Like, remember way back then, after the first midterm, like you were the only one that showed up in these office hours. I remember that.
I mean, I think I could have done better for the second one.
Uh,
I'm gonna start showing up to all my classes even after school.
oh yeah. Even after the midterms, that's good. But be like Xinyan, like she is always on the grind.
I need to
Yeah.
get back on track.
Yeah.
Well, I think I will see you tomorrow,
Yeah,
right?
I'll see you tomorrow, Xinyan.
Yeah,
Bye.
thank you. Bye.
Yeah, study hard. Just like
Mhm.
just like grind through it before,
Mhm.
yeah.
Yeah. And then you go back to Spain and rest.
Yes. Yeah, good night, guys.
Good night.
And then,
How was your day, Ryan?
oh, it was good. Wait, are you in your own apartment? It
No,
looks
no,
like it.
I'm back at my friend's. This looks familiar, huh? The background.
Yeah.
It's different than the usual one at my friend's apartment.
Uh-huh.
Hmm.
I don't know. I kind of like spiraled today, but I cleaned my room and then I like set a schedule for myself for tomorrow.
Oh yeah, that's good. Like setting the schedule ahead the day before, so you know what to do besides of like, what am I gonna do today?
Yeah, because the pool's closed and
Uh,
not a lot of it's summer break, but yeah.
did you exercise today, like with the jump ropes, calisthenics, bar,
Yeah,
and
I
stuff like
did.
that?
But the thing is that I can't do pull-ups on my door frame because my door frame's gonna collapse.
Oh really? It's that like fragile right now?
Yep.
Oh dang, that's crazy.
Yep. It's
Sorry, we couldn't get to like talk that much today because like those people had like a lot of questions.
okay. I just like sat there and just kind of like because I'm like preparing for bed, like so I can wake
Mm.
up at like 5 o'clock or 6 o'clock to like exercise.
Thing following the Mohammed schedule.
Yep.
Yeah. Hey,
Mm.
I see. Yep. Well,
I
I'll
hope.
probably see you tomorrow or something.
Yeah, I'll be here
Yeah.
tomorrow.
Mhm.
I'll just be like patient, just like waiting for everyone to leave, or like or just like everyone is just like not just done with their final.
Done with the final, right? And after that, we can like talk more about like non-related
AP
school
Cam,
things. AP
yeah,
Chem, yeah.
yeah, help me, yeah.
Right.
All
Yeah.
right, bye bye.
Yeah. See you, Ryan. Bye.
Have a have a good day. I mean, have a good night.
Yeah. You too. Sleep well. Sleep well.
You sleep well. Bye bye.
Bye.